So I wanted to do my part to help try to educate people about what's going on with this whole containment, isolation, quarantine thing that we have going on as an epidemic nowadays. Spread of a disease is actually something that we can model using a differential equation. So what I'm going to try to do is leave out as much of the complicated math stuff as possible and try to explain this in such a way where it's digestible by as many people as possible. So what I'm going to do is model the spread of a disease and then talk about some of the things that we see in the media nowadays. So I'm going to define a variable. I'm going to define P. I'm going to let it represent the number of people infected. In order for the disease to spread, that means that we would need an infected person and a non-infected person to interact with each other. So typically the way that we model this is we say let C represent what's known as a carrying capacity, basically a maximum possible population for the spread of a disease. Maximum population. That means that the rate at which it spreads is going to be proportional to the product of those that are infected and those that are not infected. Now, I realize not everybody who watches this video is going to be up on calculus, but I did want to let you know that the derivative of P with respect to time would be the rate at which the disease is spreading. Is proportional to means that it'll be a constant times the number of people infected, which we defined as the variable P, and the number of people that are not infected. If C represents everybody and P represents those that are infected, then C minus P represents those that are not infected. For the purpose of numbers, what I've done is set up the following right behind me, and I'll show you in just a sec here. We're going to assume for a second that the total population of the world is 25 people. And we're also going to assume that initially one person is going to be infected. So essentially what we have here is this represents 4% of the world population being infected by a thing. Doesn't really matter what that thing is. Could be the flu, could be coronavirus, it could be an infectiously positive attitude. This differential equation can be solved. Now what I'm going to show you is the solution of this differential equation, and then I'm going to show you some graphs, similar to what you've probably seen with the media recently. So the solution of this differential equation looks like the following. It is a separable differential equation, so we start by separating the variables, perform a partial fraction decomposition on the left-hand side, and integrate with respect to whichever variable is appropriate. We see some natural logs pop up, and exponential growth and decay should be part of this process. So with that in mind, we continue to solve for the independent variable, solve for the dependent variable, plug in the initial condition, and then do some extra algebraic jumps to eventually solve for the population. This is known as a logistic growth model. And I've taken the liberty of going over to one of my favorite graphing softwares, Desmos, and actually plotting this thing. So on Desmos, if left unchecked, then this is what your infection model looks like. As you can see, it does not take very long for a disease to spread from only one person to essentially the entire population. This would be what would happen if we let this thing go completely unchecked. Now, I did plug in a value here that is unknown, and that's the value of K. K represents essentially the rate at which this thing spreads. If we decrease the value of K, we see it spread considerably slower, and if we increase the value of K, we see it spread considerably quicker. Now with that in mind, we've been advising people to stay in a quarantine for a total of 14 days. What I did is I said, let's assume for a moment that After 14 days, the virus is gone. You are now cured. Sorry, this is kind of shaky. Let's assume for a second that after 14 days, the virus is gone and you are cured. This is what that model would look like. Essentially, I took our initial model and then subtracted a 14-day lag on it. Please watch what happens when I mess with the value of k. Once again, if I start making the value of k smaller, what happens is exactly what we've been told in the media that we want to have happen. We are lowering the curve. We are spreading the curve out. The way that we do things like that is by using quarantine, isolation, making sure that it doesn't spread as quickly. Literally, the only thing that I've changed here is the value of k. I've made it smaller. Societally, how we make the value of k smaller is by social distancing, making sure that we're not touching our faces and whatnot. Listen to them. They want to help you flatten this curve. The model doesn't change. The value of k can, and it begins with you.